In this work, we present a method to characterize the personalized spine and torso stiffness of subjects suffering from adolescent idiopathic scoliosis, using a differentiable biomechanical model of the torso and solving an inverse design problem. Our method consists of three main components. First, we have designed an experimental setup that allows us to capture controlled force deformation data of the torso and the spine. Second, we have developed a model of the differentiable biomechanics of the torso. With this model, we can efficiently map position estimation errors to desired changes in model parameters. And third, we have developed an optimization procedure that estimates parameters from the force and image data using differential formulations of both the biomechanics and the image generation process. The experimental setup consists of a way to register both force and deformation data at the same time. We capture a sequence of radiographs and at the same time a force is applied on the ribs of the subjects, gradually increasing until a comfort limit value. Their pelvis is fixed in space and their shoulder is constrained by a wall fixed in the X-ray bed. Thus, we end up in a configuration imitating the three-point pressure system, a basic principle used in scoliosis brace design. Using force and moment equilibrium conditions and body measurements, we can estimate the reaction forces on the shoulder and pelvis. Here we present an example of the radiographs capturing the spine deformation. The force readings were registered along with the radiographs. The differentiable biomechanics model is initialized from a template. The model consists of the pelvis, the lumbar spine, the thoracic spine, the rib cage, the costal cartilages with the sternum, the bones in the shoulder joint, and the soft tissue. The bones provide the skeletal part of the model, and they are articulated between them, creating a multi-body dynamic system. The soft tissue is coupled with the rigid bodies and simulated with FEM. We chose to include these parts of the body in the model as they are the ones that participate in the transmission of forces from the brace to the spine. Starting from the template model, we personalize the geometry based on frontal and lateral low-dose radiographs captured in a resting pose. We develop differentiability of the model. Please see the paper for the details. This is an example of the formation of the full model under the forces applied in the experimental setup, which imitate the three-point pressure principle. Here we focus on the deformation of the spine. To this point, we have described the development of the torso model and the personalization of its geometry. Next, we discuss the personalization of the stiffness response. We start from the captured radiographs, and we track image features of the vertebral bones in 2D. As all vertebrae have different sizes, to facilitate direct comparisons, we introduce a reference 2D box. We extract the rigid transformation of the vertebra using the singular value decomposition, and we apply this transformation to the reference box. As a result, we obtain target features Z hat. We follow a similar process for the simulation of the spine. We compute the oriented bounding box of each 3D vertebral bone. We project this box to 2D, we extract its rigid transformation, and we apply it to the reference box. As a result, we obtain simulated feature Z. Now, the target and simulated features can be directly compared, as they are both created from the same reference box. We obtain the optimal stiffness parameter by minimizing the error between target and simulated features across all vertebrae in all input radiographs. As discussed in detail in the paper, we leverage the differentiable biomechanics model in this optimization process. Finally, we present the results of our method for the 7 subjects that participated in the study. For each subject, we validate the accuracy of the stiffness estimation on a radiograph not used for training. Here we show the overlay of the torso and spine simulation using the fall stiffness parameters obtained from the bibliography. The mismatch is evident and the torso and the spine appear too stiff. Here we show the overlay with our estimated parameters. Recall that this radiograph was not used in the optimization process. Next, we show the validation results for the rest of the participants. Across all participants, the average error per vertebra feature is 3.3 mm. Thank you for your attention.